What I wanted to talk to you about is how little I think we have still done with microfluidics, in spite of all the great possibilities that there are. This is the excerpt from the talk of Richard Feynman in 1959, which is almost 55 years ago, and he concludes by saying that there are many potential applications. And so 50 years later, I still don't have this watch that analyzes my blood continuously and tells me that I need to go to the doctor or something else very interesting. There are a lot of applications of microfluidics that work, but I think that the potential is really very big. And in order to make that work, what we really want to do is to do chemistry in microchannels. There's a lot of people that worry about making droplets, for instance, etc., which is tremendously fun physics. But if we want to make this magical watch that analyzes my blood, I need to do all kinds of biochemical reactions on a chip that allow the watch to decide whether I'm doing well or not. And so I will just tell you, instead of going very deeply into a specific subject, some of the crazy, stupid stuff that we have done to try and do chemistry in microchannels. And so if I want to do chemistry, I need to do a number of operations. I need to pump, I need to mix and stir, and so I'll tell you a little bit about that. What we really want to do is also to be able to follow chemical reactions, and microfluidics, as I will show you, are an extremely good instrument to try and do that in great detail. And then if one wants to do serious chemistry, as we've seen in the beautiful previous talk, 99% of the interesting chemical reactions for industry, in any case, are catalyzed, and so one needs to think about catalysis in microfluidic channels. And so you've just had your coffee break for it's actually, Mikael, no longer the morning session, it's already the afternoon session. And you haven't realized, or perhaps you have, that in order to stir the sugar in your coffee, you use inertial forces. And so the inertial forces scale with the mass of the system, and so if you make your coffee cup larger, it becomes easier to stir in the sugar. But if you try to do that in a microfluidic channel, your inertial forces are so small that you won't be able to do that. And if one then takes the book of Patrick Tauling, for instance, one learns that the other way of mixing is, of course, diffusion, but diffusion is terribly slow. And so if you take typical values for sizes of a microchannel and diffusion coefficient of the sugar into the coffee, for instance, one immediately calculates that one needs a 1 meter long microchannel in order for good mixing to occur, which is not very practical in many situations. And so I wanted to look at mixing, and so as you've seen also in the previous talk, in many practical applications, there's first a micro mixer and then a micro reactor. What I thought was, so maybe I can use the chemical reaction itself to try and mix, because if I take a violent chemical reaction, I should create some sort of turbulence or something like that that would mix the two reactants. And so I did something that in my chemistry classes I was always completely forbidden to do. The first thing they tell you if you walk into the chemistry lab is never pour water into a strong acid solution because it will explode. And so I thought, well, this should be the correct way of mixing two things in a microchannel. And so this is exactly what we did. The disclaimer is don't try this at home, because indeed, if you do this at large scale, it will explode. And so what we do is we put water in one channel and concentrated hydrochloric acid in another. And to the water, we've added some fluorescent marker, fluorescein, to be able to visualize this beautiful turbulence that I was hoping would emerge. And much to our surprise and perhaps disappointment, we saw something that we absolutely did not understand, but that didn't look like turbulence at all. So this is the water with the fluorescein. This is the strong acid. And so what happens here, we realized after talking to a couple of real chemists, is that the fluorescence intensity of the fluorescein depends strongly on the pH. And so if you add also fluorescein, sorry, this should be HCl. If you add also fluorescein to the acid, it no longer fluoresces. And so what you see here is something that is actually very interesting, maybe even more interesting than mixing in microchannels. What you see here is the protons diffusing from the acid into the water and killing the fluorescence. And so this is a way actually to measure the mobility of protons. And the mobility of protons is something that is very subject of very lively discussions in the water community. And so by simply plotting the extent of the region from which the fluorescence has disappeared and then squared, because it's a diffusion process, as a function of the distance after the junction, I can immediately get a diffusion coefficient for the protons. And this is actually something that is extremely hard to measure in any other way. And so proton diffusion, I found this lovely movie on Wikipedia. Proton diffusion is very strange because it doesn't require mass transport. The water people think that this is actually what happens. It's just a hydrogen bond that flips from one molecule to another. And so this requires a very specific orientation of the water molecules with respect to each other, but if that orientation is respected, proton diffusion can be much faster than diffusion of any other species, simply because it doesn't require any mass transport. And so what we thought is, well, maybe if we can prevent the rotation of these water molecules, and there are certain hydrophobic groups that are known to inhibit these rotations, we should be able to slow down proton transport tremendously, provided this is the mechanism. And this is also something that was subject of discussion. And so we found one of those molecules, tetramethyllurea, that is supposed to hydrate the shell of water molecules. And so if you put enough of that molecule into water, all the water molecules have a certain orientation, and that should slow down tremendously the proton diffusion. And it does indeed, so you can immediately see that on the fluorescence images of the microchannel. This was our original proton diffusion. This is with the same flow rates in both channels with the TMU added. And so the TMU, if you do the image analysis, indeed slows down the proton diffusion by something like 1 order of magnitude. And so that is very interesting, because I can now go back to Feynman and challenge Feynman. Feynman said there's plenty of room at the bottom. Is there plenty of room at the bottom? If you go to a system that is of interest of many people here, especially those from Curie, we know that this is, again, a Wikipedia drawing of the interior of a cell, and the interior of a cell is tremendously crowded. If you would centrifuge E. coli, Wikipedia states that you get something like 300 to 400 grams per liter of macromolecules. And so proton diffusion in such a system might also be much slower than it actually is in pure water, and that has tremendous repercussions for reaction rates in the cell, because proton transport is extremely interesting again for transport and energy in the cell. And so I will show you some very recent measurements of Ines. Ines should be here somewhere. She's hiding all the way in the back, where we actually simply use the same method to measure proton mobility, but now in something that looks like this. And so this is our reference measurement. The problem is, of course, if you try to approach more or less biological things, you can no longer use concentrated hydrochloric acid, so we needed to make sure that we can still do the proton mobility measurement between pH 5 and pH 7, which is 10 to the minus 5 and 10 to the minus 7 in concentration of protons. This is not at all evident that this would actually work this well, but it does. And so what you see here is for different flow rates, again, the extinction of fluorescein, now in the bottom channel, because it's being invaded by protons from the upper half of the channel. And so what our biochemist friend Gertien Smits makes for us, we call cell soup. And so it's basically a cytosol mimic. And so the cytosol mimic indeed shows a much slower proton transport than does pure water. This is again all at the same flow rate. If we add a number of proteins to our cell soup, we actually get a diffusion coefficient that is even smaller. And so the great thing about this microfluidic method is that we can actually quantify everything. This is again last week's results, but it clearly shows that the water diffusion coefficient, the proton diffusion coefficient in water is more than an order of magnitude higher than in the cell soup, which is again more than an order of magnitude higher than it is in the cell soup with proteins. This is not a viscosity effect. So the viscosity of the cell soup is actually only 3% different from that of the pure water. Here we probably do have a contribution of the viscosity, but again the decrease of the proton mobility is much stronger than you would expect on the basis of the viscosity alone. Another strange observation is that these lines don't seem to go through the origin. They don't have to if the process is not really diffusive, and there are lots of other evidences that proton transport in complicated systems may not be simply diffusive. So this is something that I hope Ines will be working on for the next couple of weeks or month to solve all these interesting problems behind this. This doesn't solve my problem of mixing and stirring. I'm still convinced that if I find the correct chemical reaction, that I could use the energy of the reaction to actually stir and mix, but I haven't been able to find one. And so if there's a good chemist in the audience that can help me with that, I would very happily try it out in the lab. We did find an interesting way of mixing, which is if we add some strange polymers to our sauce, we can actually get, due to the elasticity of the polymer chains that are stretched by the flow, we can get something that we call elastic turbulence, and it sort of looks like this. This is a flow visualization again in the microchannel, and we can, for instance, look at the amplitude, the PDF of the velocity fluctuations in the channel, and we find that indeed, if we add only a small amount of polymer, this is 0.7 grams per liter, we have lots of very large velocity fluctuations, something that looks like turbulence, and we can even look at, because again we're in a microchannel, we can look at the dynamics of the individual polymer chains, provided we mark the chains with a fluorescent marker, and we indeed see that they are stretched and unstretched by the flow continually. All this was just the initial idea that in order to follow chemical reactions, we should mix and stir. We haven't been very successful, but we can still try and follow chemical reactions. And so what we did is we didn't have a very interesting chemical reaction, but it's a very simple acid-base. It's pyrrolidine with acetic acid that forms pyrrolidine acetate. And we choose this very specific chemical reaction because it has a very strong signal in the infrared. Basically, the bond vibrations change quite a lot, and that allows us to follow this chemical reaction by a spectroscopy method. And so again, we have the same conformation. We have pyrrolidine in one channel, acetic acid in the other, and we hope that they encounter each other and do chemistry together. This is what I just said. What we do is something called CARS. CARS is simply an extremely expensive but very rapid and very efficient spatially resolved method to do infrared spectroscopy. And so this was done with the group of my brother, who's now at the Max Planck, and Michiel Müller is actually the guy who made the setup. And so what you get is a Raman spectrum. The Raman is much more interesting than the infrared because you want to have walls in your microchannel, and the walls are usually not transparent for infrared, and they are for visible light, and that's why we do Raman. And so these are the Raman signals of the acetic acid, of the pyrrolidine, and of the pyrrolidine acetate. And you see that they are very, very different, and so this will allow us to look in the channel and see whether we have this, this, and this, and even one can quantify the amounts, how much we have. And so this is what it looks like. This is the map of the acetic acid. This is the map of the pyrrolidine. So acetic acid, sorry, this is the other way around. The acetic acid is in the upper half of the channel, the pyrrolidine is in the lower half. And then if we look at a different wave number, at a different absorption frequency, we can actually get the product. And what we see is that the more we go downstream, the more product forms. And so this is great because we can actually follow the chemical reaction in time by looking at different downstream distances. The CARS microscope is actually very, very nice. We have something like 400 nanometer resolution, 0.4 micron in the XY plane. And CARS is very nice. It's much nicer than Raman because its quantum yield is much, much higher. And so we can get one of these maps typically in something like a minute, whereas it would take something like a month if I had a good Raman spectrometer. One of the surprises or not surprises is that, again, by looking at different downstream distances and looking at, for instance, the concentration of product, one can see that the product formation is, again, diffusion limited. This is the total concentration. This is the square root of the distance, which is the square root of time. And so it's, if it's square root time, it's simply a diffusion of the two reactants that form the product. And so this is something that we've all learned in high school or perhaps somewhat later, that chemical reactions in general are diffusion limited. If you look into the literature, you see what evidence there really is for that statement. There's actually very little. And so this is a relatively cheap and relatively easy way to actually see that this is the case. You can even do a sort of, for instance, COMSOL simulation of this diffusion process, and then you can get maps of the concentration that actually closely resemble that for the experimental, from the experimental CARS spectra. This is, of course, not extremely interesting because this was a very stupid and very basic acid-base reaction. However, the promise of this technique is that you can do much more complicated reactions, that you could actually quantify the much more complex dynamics, for instance, for a catalyzed reaction or a second order reaction. And even the infrared technique would allow you to to identify reaction intermediates that are normally very difficult to find in a batch reactor because they only exist for a limited amount of time. And here, by looking at different downstream distances, if you first form an intermediate product before forming the end product and they're sufficiently different in their car signal, you could actually try and identify what reaction intermediates are, and that is in principle very interesting for a lot of chemistry applications. Last point, if one wants to do chemistry, one needs to do catalysis, because normally one doesn't go over the reaction barrier mountain, but one goes around it. I don't know why this car with molecules actually goes through it. You hardly ever tunnel through the energy barrier, but you could go around again by forming some reaction intermediate that has a lower activation energy. And so I think that everything you saw in the first talk, I forgot to ask, was homogeneously catalyzed, namely the catalyst was actually in the solution. That has the disadvantage that you will, at the end, have to separate the catalyst from your reaction products. And so ideally, you would make a heterogeneous catalyst where, for instance, the catalyst is on the wall of your microchannel. Microchannels are especially well suited for that because they have a high surface to volume ratio from the start. And so the idea was to try and see whether we can make a heterogeneous catalyst for an interesting chemical reaction. And so doing something completely different, I should have mentioned that this is with Bradley da Silva, Mehdi Habibi, Michael and Stephanie. Sorry, had a blackout. And so also at Chimie de Paris. The thing that Mehdi Habibi was doing in his lab was he was playing with glass with a silver salt in it. And it turned out that if you make a glass and you put silver nitrate in the glass while making it, you can make something that looks like a microscope cover slide, but that has this salt in it. And if you now shine the right wavelength of laser light into that glass, the silver actually comes out to the surface. This is the path taken by the laser beam. We can make anything. I've asked them to make a Mickey Mouse, but they haven't been able to program the computer that way yet. And so if you look at what this is, these are tiny little nanometric silver clusters that pop up from the surface. And that is exactly what you want for a heterogeneous catalyst. And just a simple method at the first try already gives a rather high specific surface area of something like 220 cubic centimeters per gram of silver. Yeah, and so this looks like an ideal catalyst. And then we found a simple way with Norland optical adhesive to close the microchannels. And then we found an interesting chemical reaction, which is the depollution of water. And so this is a terrible molecule which is in water. Normal water purification works with ozone. That's why the water no longer tastes like chlorine. And so the ozone is actually supposed to break down all of these terrible organic molecules by simply oxidizing them. And so what we do is we have an ozone generator. We put that into the polluted water and then have that flow through the microchannel. This syringe is actually sucking, not pushing. Flow through the microchannel, and we can see how much of the PCBA is actually destroyed in the microchannel. And so we can take some solution from here. We can have the catalytic microreactor, and as a reference we can get the microreactor without the silver catalyst. And so what we do is we, as also you saw in the previous talk, with HPLC, detect the amount of parachlorobenzoic acid that remains after treatment. And so between the batch reactor, the microchannel and the catalytic microchannel, you see that there's already a large difference. The major difference is that the residence time in the catalytic microreactor is about 100 times smaller than it is in the batch reactor. And so if you do the math, you find that the catalytic microreactor gives us a 350-fold increase in reaction rate. That is absolutely great. Interestingly, probably because of its large surface area, the microchannel without silver actually also breaks down a significant amount. We have no good idea why that happens. But we do have a very clear catalytic activity. And so with that, I've come to my conclusions. We completely by chance stumbled on a reliable way of measuring proton mobility, and so this is one of the examples where microfluidics can be extremely useful. I think this proton mobility in the cell soup is a very exciting new thing that we're going to look at. I haven't showed you the details, but we can use elastic turbulence to mix in microchannels. I don't know how useful that is, but it was fun. We found a novel method to immobilize a catalyst on the walls of a microchannel. And so it's not impossible that this could work also with even more interesting metals, such as, for instance, palladium. We're actually in the process of trying this. And the method is so interesting because we get nanoclusters of about the right size for heterogeneous catalysis. And so perhaps the largest potential is these scarce measurements of chemical reactions in the microchannels. Again, this needs to be done in much more detail because the reaction we looked at is not extremely exciting to chemists. So if there are chemists here that do have a very exciting chemical reaction to study, I would very happily discuss. Thank you very much.
I have a question regarding the first part of the talk. My question is really naive, but when you compare the viscosity of the three phases, and is it still, what I mean is the Stokes-Einstein relationship still valid when you work in the cytosol, for example?
That is a very interesting question to which I have no answer for the moment. Yeah, so the fact that these lines don't go through zero, we have a little difficulty in determining where the zero actually should be. There's no real reason why this should be normal unhindered diffusion. Yeah, and so it's only if it's normal unhindered diffusion that it should be Stokes-Einstein. So what this is, we don't know. But there's something going on that is not related directly to the viscosity, and that I think is the interesting part.